Multi-agent task allocation is the problem of determining which agents should execute which task to achieve the overall system goals. Based on whether the scheduling, routing, heterogeneity of agents, and the dependencies between tasks are considered, there are variations of task allocation problems. Both learning-based and optimization model-based frameworks have been applied to the task allocation problem. Learning-based frameworks usually require low computational costs once they are trained, and can achieve high performance in similar task environments, but they typically require a tremendous amount of training data. Optimization model-based frameworks leverage expert knowledge and generalize well to unseen task scenarios. However, these optimization frameworks often assume their task models are given. In practice, this expert information can be unavailable, and few previous optimization-based systems provide a method to obtain their modeling parameters. This paper presents a learning framework to estimate a task requirement model for multi-agent task allocation. With a small set of team configurations and the corresponding task performances as the training data, a set of linear task constraints can be learned and embedded in many existing optimization frameworks. Finally, the task allocation optimization will consider the environment setup as well as the task constraints simultaneously to generate the routes, schedules, and the teams for all of the subtasks involved. The first component of the system is a simulation or experiment that evaluates the system performances. For this, we develop a simulation example containing 5 heterogeneous agents and 5 different task types. The agents have different sensor ranges for perception, and some of them are equipped with a manipulator that can conduct pick and place tasks. The tasks include exploration, block picking, as well as block searching and picking. Each of the tasks requires multiple agents to work together. In order to learn the task constraints for the optimization, the first step is to evaluate the performance of a subset of the team configurations. Here we use task completion time as a metric to indicate the performance. Here we show 4 examples during the training data gathering stage. The first example is a cooperative exploration. Once the team is determined for the task, a simple intra-team planner separates the region into sub-areas, and the robots should scan the areas with their laser scanners. The second one is a cooperative block picking task. In this example, there are 4 robots from the same type. The blocks at known locations are greedily assigned to an idling robot until the whole task is completed. The third example is block picking with 2 types of blocks. In this specific team, the white robot can pick up both blocks, while the black robot is not able to pick up the heavier blocks. In the last example task, the agent should jointly search for a robot in the region. Once the block is found, a qualified robot should pick it up. A selected subset of team configurations is evaluated in the simulation. We can set the threshold time for each task type, and the team is considered valid for the task if the completion time is below the threshold. Suppose these red points are valid teams, we can then use a set of linear constraints to approximate the boundary. Based on this idea, our proposed learning model will estimate the task requirements specified as agent capabilities. For instance, suppose there are 3 types of agent capabilities: perception, manipulating light blocks, and manipulating heavy blocks. Then, the agent capabilities and task requirements in this table can be learned. A team for a task should possess total capabilities larger than the requested values. Finally, with the learned task constraints, an optimization-based task allocation can be used to determine the optimal teams, routes, and schedules. We show an example where 5 heterogeneous tasks are distributed in an outdoor environment. The agents should start at the depot and complete all the tasks while minimizing energy and time consumptions. According to the optimization, 1 agent number 2, 2 agents number 4, and 3 agents number 5 are enough for the whole mission. After completing all the tasks, the agents return to the depot around a similar time. Computational evaluations and more examples can be found in our paper to show that the framework is accurate, efficient, and scalable.